Hello everyone. In this chapter, we are going to study the plane autonomous systems. When differential equations do not contain an independent variables explicitly, the equations are said to be autonomous. In the present chapters, we consider an autonomous system of first-order differential equations. Especially, we will concentrate on plane autonomous system in which two dependent variables appears in equations. First section is the autonomous systems. Second section is the stability of linear systems. Last section is the linearization and local stabilities. We analyze a non-autonomous system in this section. A nonlinear system is linearized around a critical point, and we will discuss stability of the critical point. First section is the autonomous system. The following system of first-order differential equations becomes autonomous because an independent variable of t does not appear in the right-hand side of the equations. So there is no t inside of the parentheses, no t. Only dependent variables can be found in the right-hand side of the equation. So x sub 1 and x sub 2 up to the x sub n is a dependent variables. Vector form of a linear systems. So we combined some equations into a single equation using vector quantities. So x vector is expressed as a component of the x sub 1, x sub 2 up to the x sub n. All the dependent variable is a function of t. These are independent variables. And g is also another vector quantities. G sub 1 is a function of x sub 1, x sub 2 up to the x sub n. Also g sub 2 is a function of the dependent variables. So we combine some equations into the single form of the equations using the vector quantities of capital X and the g vectors. So in this case, we only consider the first order differential equation. Then you might wonder what happens if we have a higher order differential equation. Even when we study the higher order differential equation, it is transformed into some first order differential equations. Therefore, the present study can be used when we analyze the higher order differential equations. I'd like to show you the example. So in this case, we consider second order differential equations. Second derivative x with respect to t equal alpha x. Then we'd like to transform this equation into the first order differential equations. So we introduce a new dependent variable of v. This v is expressed as derivative of x with respect to t. Then this equation, original equation is expressed dv over dt equal minus alpha x. So we have a two differential equation, this one and this one. So I can write under this equation is dv dt equal minus alpha x. And also we have another differential equation dx dt equal v. So we could combine these equations by introducing the vector quantity of the capital X is a x b. Then d dt x is expressed d dt x v. So dx dt dv dt dx dt is equal to the v. dv dt is equal to the minus alpha x. So this corresponds to the gx. Like these examples, higher order differential equation is transformed into some differential equations. So in this case, second order differential equation is transformed into two first order differential equations. Now I'd like to move to the next topic of the vector field. So we consider the derivative of the x vector equals g. So especially we'd like to consider the case of the two dependent variables of x and y. So d dt equal x y equal, this is correspond to the velocity, the v sub x, v sub y. This is equal to the g vector is expressed, v is capital V is p and q. So p, capital P as a function of xy. Because the autonomous system we consider p does not contain the independent variable of t. And q as a function of xy. A vector field of the g. It corresponds to the velocity of a particles, like this. V sub x, V sub y. By following the velocity vectors in the vector field, we can find the path of particles. We draw a short arrows directed toward a vector determined by the capital P and capital Q's. So example, we have this P is expressed as this vector quantity. Then we draw a short arrows starting at the x and the y's in this vector field. And the horizontal axis is the x axis and the vertical axis is the y axis. And then we draw a number of short arrows. Then by following these short arrows, for example, if we consider the particle starting this point and then follow these arrows, you can find that this could be the path of particles. So without solving the actually differential equations, we could find the solution curve of differential equations by following the vector field. The differential equations has three types of the solutions. First one is a constant solutions. So this means x, capital X prime equals 0. So this means gx equals 0. So from these derivatives, you can find that the x is a constant quantities. X is a constant component x sub c, y sub c. So we call the constant solution, we call the critical point, a critical point. So to find the critical point, you could solve this gx equals 0. Another solution is the arc. An arc is a curve that does not cross itself. If the particle is starting from here, and the particle might move away from the central point, or this arc is opposite directions. Sometimes even if we consider the particle is here, particle might approach to some point. So this is another solution of arc. Another solution is a periodic solutions. A particle in a curve cycle around the curve. So if the particle is starting here, particle is moving around and return to the original point. So this is a periodic solution. So we could have three types of solutions. Then I'd like to explain a little bit more about critical point. There are two types of the critical point. One of them is a stable critical point. The other one is an unstable critical point. So we consider the initial point near a critical point to place a particles. There are two possibilities. In the first case, this is the initial point. Particle is approaching to some point. So in this case, is asymptotically stable critical point. So this critical point, expressed the blue point, is a stable critical point. Because if we consider another particle is approaching to the critical point. Or particle does not approach to the critical point, but moving around the critical point. This situation, periodic solutions. Also in these cases, this critical point, blue point, is a stable critical point. Then the other case, unstable critical point. I show the two critical points, red one and the blue ones. Even if we place the particles near the red critical point, this particle does not approach to the red critical point, instead is moving away from the red critical point and moving and approaching toward the blue critical point. So in these situations, even if you place the particles close to the critical point, particle does not approach to such a critical point. We call such a critical point is unstable critical point. In the next section, we are going to study the stability of a linear system, and we are going to find out unstable critical point or stable critical point. Okay, this is the end of this session.